Welcome everyone to today's T-CAIREM training round presentations. We are excited to welcome some talented speakers and also extend a warm welcome to today's three adjudicators who will be providing us with some valuable discussions and questions. We're welcoming Christopher Sun from the University of Ottawa Health Institute, Kamil Uludag from University of Toronto, and Eric Bentramal from the Hospital for Sick Children. So today we're going to be hearing from two very talented trainees who will be each presenting for 20 minutes, followed by a 10-minute period with Q&As. First up, from 12 to 12:30, we have Austin Barr presenting on zero-shot generation of synthetic neurosurgical data. Following that, from 12:30 to 1 p.m., we'll be hearing from David Mikhail, who will be discussing multimodal performance of GPT-4 in complex ophthalmology cases. So let's start with our first presenter, Austin. Austin is a medical student at the University of Calgary and currently serves as the president of the school's AI Society. His research focuses on the generation of high-fidelity synthetic clinical data. Before medical school, Austin was a program officer at the Canadian Institute for Advanced Research, where he contributed to the Pan-Canadian AI strategy. He also has a background in clinical research from his time at Sunnybrook Hospital's Research Institute and holds a BSc from McMaster University, where he helped design, implement, and teach an introductory AI course. So please join me in welcoming Austin Barr. Austin, you have 20 minutes for your presentation. Over to you.
Awesome. Thank you very much. Can you see my screen?
Yes.
Perfect. So first of all, thank you very much for the opportunity to speak today. I watched the trainee rounds last year and I've been really enjoying the presentations this year as well. So very grateful to be a part of it. And thank you, Julia, for the introduction. So yes, I'm Austin, a medical student at University of Calgary, and I'll be presenting on some of my work regarding the generation of synthetic neurosurgical data. Okay, so first of all, what is synthetic clinical data? So synthetic clinical data is artificial data that is generated with the intention of retaining key properties of a real-world data set, but is designed to preserve patient privacy because it isn't directly linked to real patient records. So ideally, it has three properties. It's, first of all, statistically similar to real data, so it has what's called fidelity. Second is it doesn't include any patient identifiers or the ability to extract sensitive information associated with a real patient, so it's privacy preserving. And third is that you can use it in place of real-world data for any number of downstream tasks, so it has utility. And just note that synthetic data can take many forms. It can be tabular data, text-based data, imaging data, really any type of media. But today I'll be specifically discussing tabular data. And so an important question naturally arises, namely, why not just use real-world data? And more specifically, what is the impetus for synthetic data? So I'm going to provide a number of reasons, but I think the easiest answer is that for anyone who has ever dealt with a data sharing agreement or an RAB application, I'm certain that you'd appreciate a more efficient alternative. So real-world data, and particularly sensitive clinical information, is constrained by privacy regulations, and for good reason. If you want to access, share, or use this data, there are significant hurdles you have to overcome. So processes like research ethics boards, data sharing agreements, compliance with privacy regulations, and de-identification procedures. They're all complicated, they're time-consuming, and they're resource-intensive. And so because synthetic data is artificial, it isn't necessarily subject to these same restrictions or steps to access, share, and use it. So the next answer to this question lies in many of the inherent limitations associated with real-world data. So clinical data, which is either routinely captured during patient care or is intentionally collected during research initiatives, are often incomplete, so missing information. And for many reasons, it could be that the clinical variables may have not been recorded, patients may have been lost to follow-up, or in the case of a study, there may be participant attrition. So data sets also may not be homogenized between sources. So it could be in format, it could be in the available variables. Sample sizes may be too small, which is often the case for rare intracranial diseases and single center data sets. And this can result in insufficient statistical power, inability to reasonably train an ML model, and insufficient data to adequately reflect a population. And sometimes data just may simply not be available. And all of which may have the potential to be addressed with synthetic data. And finally, the last answer to this question is the de-identification procedures. So pre-processing and de-identifying data sets is laborious and often requires removing or obscuring information which may be relevant for analyses. So features like demographic data, geographic data, and temporal factors. Similarly, de-identification may also limit the granularity of data which can be reported. So a good example of this is if you were to use an ICS data set, anytime there are 5 or fewer cells of data, these are suppressed. And lastly, it's also just worth noting that de-identification procedures are obviously not infallible. So in our study, we were investigating whether we could generate high fidelity, privacy preserving synthetic perioperative neurosurgical data um, using a generative adversarial network and a large language model. And we were doing this to do 3 things. The first of which was to augment a real-world data set with a limited sample size. The second was to use the synthetic data sets in place of real-world data for clinical analyses. So specifically to look for significant clinical predictors of postoperative outcomes. And third, to use the augmented synthetic data sets to train an ML model to predict deterioration at discharge on the real-world data. So we used a real-world data set consisting of records from 140 neurosurgical cases conducted on older adults with several preoperative, intraoperative, and postoperative variables. So these ranged from age or BMI to comorbidity indices to the specific histology, which required neurosurgical intervention, to what's called the Milan complexity scale, which involves a number of operative variables to, generally speaking, measure the complexity of the operation, and Karnofsky performance status, or KPS, deterioration at discharge. Now, KPS is a measure of a patient's functional status, and the lower the score, the lower the patient's independence, and the greater their need for care. So if this were to deteriorate at discharge, meaning the patient's KPS was lower at discharge than it was preoperatively, then the patient lost some level of function and independence. And so using this real-world data set and the listed variables, we were investigating whether we could generate associated synthetic data sets at the same and at amplified sample size using both a GAN and an LLM. Okay, so there are several different methods that you can use to generate synthetic data. One method, which is relatively well established in the literature for tabular data specifically, is the Conditional Tabular Generative Adversarial Network, or CT-GAN. So to pre-process the data set for use with CT-GAN, we normalized continuous parameters and numerically coded categorical variables. We then analyzed the loss functions to determine the optimal number of training epochs, and then generated 2 synthetic data sets. So one of the synthetic data sets was at the same sample size as the original real-world data set, and the second amplified data set with 1,000 synthetic patients, so an amplified data set. Next, we attempted to generate synthetic data with the LLM GPT-4o. And as you'll see on the slide here, we prompted GPT-4o with a plain language summary of the statistical properties of the real-world data set. So to do this, we summarized the univariate properties of the real-world data set, including means, standard deviations, ranges, and proportions, depending on the variable type, as well as bivariate relationships, so Pearson's correlations. And we specifically noted any correlation coefficient with an absolute value greater than 0.2, and then included all of these statistical properties in a plain text prompt. And it's really important to note here that we didn't provide any real-world data to the LLM. So what you're seeing here in terms of the prompt is the only thing that the LLM received. Similarly to CT-GAN, we generated 2 data sets at same and amplified sample size. The only adjustment that was made to this prompt for the amplified data set was just changing the desired sample size from 140 to 1,000. Okay, so just so you have a general idea of what was outputted from the LLM, it was a downloadable Excel file with 13 columns, each of which corresponded to one of the instructions in the prompt in the previous slide. And the generated data sets were complete and appropriately structured. Now you'll notice that parameter names like age or BMI were obfuscated to X1, X2, X3, etc. And the reason for this was to ensure that no biasing occurred either from contextual cues from the parameter names or from any potential exposure to this data set as training data. But we'll see in a minute that all generated records were unique. There were no exact row matches to the real world data, so no concerns there. The first column X1 was a log transformation of age because the variable was not normally distributed. And so the model was also tasked with removing this log transformation in the second column X2. And we validated these transformations, and there were no calculation errors across both GPT-4o generated data sets. And in the final column, X13 on the right, we numerically coded the histology parameter to again ensure no contextual biasing. So overall, a number of different data types reflected here: continuous, ordinal, binary, and categorical, to get a good diversity of data types. So how did these data sets compare to the real world data? So first of all, after confirming that the data sets were complete, they were structured appropriately and contained unique records, we used several different methods to evaluate fidelity, but two in particular I'd like to highlight here. So first, in terms of bivariate correlations, you'll see in the table that all statistically significant relationships between clinical parameters were preserved by the GPT-4o generated datasets, both at same and at amplified sample size with appropriate direction. These were also preserved in the amplified CT-CAN generated dataset with some small discrepancies in the same sample size CT-CAN generated data. Next, I'd like to show you the second fidelity metric that I want to highlight here is that synthetic datasets not only achieve strong alignment to the original dataset's distribution of histology, but they also reflected the rarity of many of the histology, which may have only had one case in the original dataset, which I highlighted in red on the table. And so we're seeing that the respective rarity of cases are retained in the synthetic data, which was very promising. So so once we found that there was privacy preservation and that there was fidelity, the next thing that we wanted to determine was whether these data sets had downstream utility. And so the first thing we did was we conducted two analyses to determine whether we could reliably use synthetic data to answer research questions in place of real world data. So more specifically, we analyzed the synthetic data sets to look for significant clinical predictors of meaningful post-operative neurosurgical outcomes and compared the results to ground truth findings when the same analyses were conducted on real-world data. And so for our first research question, which served to reproduce an analysis which had been done in the real-world data's original paper, was looking for clinical predictors of what's called KPS deterioration at discharge, which I had previously talked about. And we found that all significant ground truth clinical predictors of KPS deterioration at discharge were retained by both GPT-4o and CT-CAN generated data sets. So you'll see highlighted in the table Milan Complexity Scale, or MCS, and complications, which were both significant predictors of KPS deterioration at discharge across all three data sets. The next analysis that we conducted, we asked a new research question as an extension of the previous study. So in particular, we were looking for clinical predictors of a post-operative ICU stay greater than 1 day. And we found that the GPT-4o generated data, again, retained all significant ground truth clinical predictors, namely preoperative KPS and complications. But in this analysis, we observed a little bit more variability with the CT-CAN generated data. So next, we were interested to see whether we could use the augmented synthetic data sets to train an ML classifier to predict KPS deterioration at discharge on the real world data. And this is known as a train synthetic test real task. And it's a fairly standardized utility metric for synthetic data you'll find in the literature. So you'll see the confusion matrices here for models trained on both the GPT-4o generated data on the left and then the CT-CAN generated data on the right. And these are both the amplified data sets. Now, obviously, these are not incredible F1 scores, but what's notable here is that by simply generating an amplified synthetic data set, we were able to make an otherwise infeasible ML task possible. And I say this particularly because if you ran a cross-validation with the real-world data set using the same classifier, its average performance was worse than a coin toss. So we thought that this was quite promising. So three key points here. So first, we generated synthetic data sets which retained clinically meaningful relationships at same and at amplified sample size to real-world data. Second, GPT-4o offered a highly accessible means of generating synthetic clinical data, whereby the LLM can be prompted with plain language instructions and without inputting any reference data. And third, Our synthetic data sets with amplified sample size were capable of training an ML model, which could be applied to real-world data to help predict neurosurgical outcomes. So now I'd like to talk a little bit about some limitations. The first thing I'd like to acknowledge was that there were some differences in effect size for the predictors of postoperative outcomes within the clinical analyses conducted on the synthetic versus the real world data. However, much of these discrepancies would be addressed with further improvements to data fidelity. And furthermore, and I think more importantly, because these data sets are intentionally not meant to be identical, because they're privacy preserving, there should be some threshold for accepted variability here. Second, in future work, we'd want to conduct expert validation of the data sets to ensure all variables make sense in the context of one another clinically. And third, we'd obviously want to improve upon the ML model performance. So things like feature selection, using different models, and also validating on additional data sets. So we touched on a few different use cases for synthetic data in terms of data augmentation, in terms of training ML models, and in terms of conducting clinical analyses, both to reproduce research findings and to answer new research questions. But there are many other future directions that I like to talk about, and I've adapted this table from a really great report from Dr. Khaled El-Imam, which I've linked at the bottom of the slides. First off, as I mentioned earlier, real-world data is often missing data. It may be limited in sample size, or it may have class imbalances. And so one of the primary applications of synthetic data is data enhancement or augmentation. This may involve amplification, like I've discussed in our present work, but we'd also like to further investigate its applicability for filling in missing data to supplement real-world data sets and to simulate rare events or cases which may be underrepresented in the data. And so more specifically, going beyond merely amplifying a sample size, because this approach alone does not address limitations in data diversity or inherent biases in real-world data. Next, I'd like to discuss data sharing. So instead of the incredibly time-consuming data sharing agreements, which are necessary for multi-site collaboration, we could instead share synthetic data sets associated with collected center data to compile larger multi-site data sets, or to share for externally validating ML models. And the third application I'd like to touch on here is data retention. So we're often time bounded by our access to clinical data sets. But if you had a synthetic data set associated with real world data, this could be retained indefinitely. And one additional data sharing element I'd like to highlight as a closing thought. There's been a large corpus of literature which has demonstrated the infrequency of data sharing among clinical research, and particularly among surgical trial data. This limits research transparency, reproducibility, and opportunities for secondary analyses on data which has already been collected and cleaned. And while the International Committee of Medical Journal Editors, or ICMJE, has implemented a data sharing policy, even when data sharing requests are submitted to the corresponding author, it's rarely shared. And this has been shown in the literature a number of times. And so some of the next steps to this work is whether there could be a standardized framework whereby authors could share a synthetic data set associated with their study to enable follow-up research. So the ability to reproduce findings and to more easily compile larger data sets. And I believe that LLMs are suited for this. They don't require access to real-world data and can be prompted with plain language instructions, which largely democratizes synthetic data generation. So something we haven't previously seen with the technically involved generative approaches like GANs. And so before I conclude, I'd like to briefly thank my co-authors, Dr. Eddie Guo, who just began his neurosurgery residency here at the University of Toronto, Dr. Bridge Carmer, a neurosurgery resident and graduate at the University of Calgary, and Dr. Emery Seskin, who runs the Intelligent Futures Research Lab out of Nationwide Children's and the Ohio State University. So all three made really significant contributions to this work. So a big thank you to them all. And thank you all very much for listening and for having me. And I'm happy to take any questions now.
Thank you, Austin, for that insightful presentation. So now we have 10 minutes to open up to our adjudicators. Please feel free to raise your hand or just ask your questions directly.
I can perhaps start. Austin, great talk. Can you go back to the confusion matrix, please? I didn't fully understand. Can you just walk me through very quickly what you are showing here?
Yeah, of course. So you can see here, there's sort of true label and then predicted label. So the predicted is what the model, the classifier predicted. So whether it said it was not going to be a KPS deterioration or KPS deterioration at discharge, so 0 or 1. And then true label would be whether or not it got it, whether or not the it's a positive or a negative. So whether in actuality that case was a KPS deterioration at discharge or not a KPS deterioration at discharge. And so you can see when they align, it's true positive or true negative. And then down here you'll see the F1 scores, precision and recall, and I can just pull up. I have in the appendices here, if this helps as well. Just the formulas here. So it's like F1 score and then recall and precision in terms of the
Yeah.
formulas there.
Yeah, so I was wondering about fidelity. You have shown a lot of analysis and so on, but I was wondering whether perhaps the best way, not the best way, but one way of to assess fidelity would be sort of to force a classifier, not necessarily what you have done, but to force a classifier to say which one of the data is most likely artificial, which ones are not. Let's say put out the 10 most artificial data. I don't know, perhaps you have done this. And then if it's then the generated data, the synthetic data is done very well, then the ones which are forced to be where your classifier says artificial, it would be equally represented by real data and artificial data because it cannot distinguish. So would this not be the fidelity test which you would need to do?
That's a great question. And it's actually very similar to the architecture of the GANs, right? So I haven't conducted this analysis on the synthetic data generated with the LLM, so the GPT-4o, but it's very similar to the architecture of a generative adversarial network in that you have a generator and then you have a discriminator, and then the generator creates data, and then the discriminator has to predict whether it's real or synthetic, and then it trains for a while, and then eventually it's able to fool the discriminator, and then you know that you have decent synthetic data, at least in that regard. So yeah, it would be interesting to look into. I haven't seen that done before necessarily, but I'm certainly going to look into the literature to see if that's been done for other types of synthetic data. That's a great question. Thank you very much.
Yeah, because for a lot of real data, it's very, very difficult to mimic the statistics of real data, even if it finds a way, especially if you have limited data, it finds some idiosyncrasies and can generate real looking data, but there's still something missing. And then, so if you then force a classifier to say the top 10%, which are most likely synthetic, and if it's done very well, then it would be there would be real data in that classifier. So therefore, I think that kind of test would be probably good, especially if you then go perhaps away from tabular data or more complex tabular data. It might be useful to involve such kind of a test for fidelity. Otherwise, not otherwise, but I really like your talk. It was very good to follow and very interesting results.
So thank you very much, and thanks very much for going through that suggestion. That's a great thing that I'm going to be looking into later today. So thank you.
So I can ask the next. Actually, I have two, so maybe I'll ask one, and then if we have time, I'll come back to the other one. Can you actually go back to your what we call the 2x2 tables that you just showed? And sorry, I'm coming from a clinical medicine perspective and clinical epidemiology, so some of the terms that I use are going to be a bit different. We call this a 2x2 table. Yeah. So precision in clinical medicine, we call it positive predictive value. You've got precision of about 60%, and precision really depends on the prevalence of the outcome in the population. And so your prevalence here is, I'm just trying to read. So it's on the left, it's 37 plus 4, right? Out of 100 and something patients.
Yes.
So,
It's not an insignificant prevalence. It's a fairly high prevalence of this outcome in this particular population, and yet you've got a precision of about 60%, which is a bit worrying. So,
Correct.
what is the implication of having a precision that low, and then applying this machine learning classifier to a larger population? What do you think will potentially happen? Like what is the either resource implication or clinical implication or social burden on the patient, for example? What are you worried about here?
Right. I understand. I understand where you're going. It's a really important point. I will just sort of preface this in saying that this is not a classifier that we would necessarily use in clinic.
Mm-hmm.
So the task that we did which is called the train synthetic test real task, is more so to show that it has fidelity. It's more of a fidelity metric than it is a utility metric. In that it's more so showing that there is some ability to use the data, but more so that it has some relevance to the real world data set that it's coming from. So this is a fairly standardized utility metric, as I mentioned, that you'd find in the literature that people use to assess the quality of synthetic data. And so, to your point, yes, this is obviously not, as I said, like the greatest performance of an F1 score or of precision, but it was more so illustrative that there's some fidelity here, one, and then second, that when you augment the data, so you amplify the sample size, you're able to apply it to an ML task, which you otherwise wouldn't be able to do with a very small data set of 140 patients. I hope that answers to some
Yeah,
extent.
yeah. I mean, so it sounds like what you're saying is this is showing that there's some replication of the real world data, but it's
Correct.
not perfect. And I guess, yeah, my concern would be with that level of precision is that you're going to have a high degree of false positives.
Right.
And so your synthetic data may falsely, whatever the outcome is, which in this case is fidelity, but whatever the outcome is, your synthetic data is going to end up with a bunch of people being screened as having but not truly having it, right? Like not truly,
Yes.
they wouldn't otherwise have been in the real world data. They're not the same.
Yes, 100%. The other thing is we just threw a binary classifier at it to show the fidelity because it's more just about the fidelity metric.
Mm-hmm.
But obviously, if this was more towards a clinically facing model, we would have done some feature selection. We would have played around a little bit more with the weights. We would have been a little bit more selective with the model that we chose. But it was more so this is a standardized metric that people tend to use for synthetic data itself. So, but yes, 100%. This is not something that I'd want to put into a clinic. Certainly not as of now. But so thank you very much for
Perfect.
addressing that
I have a
point.
second question, but I'll wait because we're running out of time. So
Yep.
Perfect.
Chris. Yep. Perfect.
Yeah, I'll try to be quick too. Excellent presentation. I think you did a great job clearly describing the problem. It's a challenging problem, so kudos to trying to address it. I think some of these are more comments than questions, but curious to hear your thoughts.
Sure.
So effectively, from my understanding, the way that three motivating factors to synthetic data can kind of be boiled down to imputation of missingness, some form of statistical preservation, and then you also highlighted a case of like improving downstream predictive model performance, right? And you kind of had results, maybe not so much on the imputation part of missingness, but for the other two, surely. I think uh, first question is, have you thought about benchmarking against maybe more classical methods of solving some of these problems? So an immediate one that comes to mind for predictive performance is like, for example, oversampling. Would
Okay.
that be enough, or how does that compare to your GANs or LLM approach?
So,
Yeah, go
oh,
ahead.
sorry, no, finish your thoughts. Sorry.
Yeah, so and this could also be extrapolated to imputation, like how does mice do, or all of these, like even the naive median. I think for statistical kind of preservation of findings, I'm not as familiar as what would be an appropriate benchmark, but I think certainly demonstrating how much your approach improves across these things for each of these specific tasks would strengthen the design.
No, that's a great point. And as you mentioned, we didn't necessarily do too much with missing or incomplete records. It was more so just amplifying the sample size. And so I'm not as familiar with these metrics in terms of how they perform with this because we didn't perform it with the GAN or with the LLM. But that's certainly a next step that I'd like to take with this work. And so, yeah, thank you very much for another great idea on next steps on this. But yeah, that isn't something that I'm super familiar with just because we haven't conducted that analysis as of now.
And I think it's exciting work. So I think you'll have a multiple future directions. And I think the only other thing is I think on one of the slides with the statistical results, it did seem like you did preserve, I think, the major ones, but I think some of the significance like did show. I think it was on slide 14 or something, like the
This one?
uppercase, yeah.
Okay.
Like for the LLM
Yes.
and CN, like the p-value is statistically significant for age. I think this is natural, but it might be helpful to like point out, presentation wise that there's still like ongoing work. There's some differences that you still need to
Yes.
design. Yeah.
Yeah. Thank you.
But yeah, great job.
Thank you.
Awesome. Thank you, Austin, and to our adjudicators for that engaging discussion. So let's now move on to our second presenter, David Mikhail. David is a second-year medical student and MSc student at the University of Toronto. His research explores applications of deep learning in ophthalmology and surgical education with a focus on retinal disease detection, glaucoma screening, and developing objective methods to assess cataract surgery proficiency. David, you have 20 minutes for your presentation. Over to you.
Wonderful, thank you. And let me know if you can see my slides.
Yep.
Perfect. All right, so hi everyone, I'm David Mikhail, second year med student at U of T. I'd just like to thank T-CAIREM for the opportunity to present today. I'm also one of the summer students, which has been nothing short of an incredible experience, as I'm sure the audience can attest to. So today I'll be discussing our study assessing the performance of GPT-4 in real-world complex ophthalmology cases. And I'd like to thank my co-authors for their support on this study. So when we think of AI, we often think of traditional machine learning models, which are trained on expert-labeled data to perform a very specific predefined task. Many studies exploring AI in ophthalmology apply deep learning models, specifically convolutional neural networks or CNNs, for image-based diagnosis, either binary, meaning sort of a yes or no for pathology presence, or multi-class, where the model is trained to distinguish correct diagnosis from a host of other pathologies. We've most commonly seen these models applied to retinal disorders like diabetic retinopathy, age-related macular degeneration, retinitis pigmentosa, epiretinal membrane and macular hole, but also for other diseases like glaucoma, where early detection is essential to preserve patients' vision. It's important to note that these models actually perform very well on their specific tasks, with some meta-analyses reporting close to perfect pooled performance metrics. Foundation models, on the other hand, shift how we think of AI development from being task-specific to versatile. These are large-scale neural networks trained on large amounts of unlabeled data using self-supervised learning and transformer architectures, where a single model can be fine-tuned to a wide variety of downstream applications. Foundation models are grouped by their training data. You've got your large language models, which are foundation models trained on text. Vision language models are trained on images, and multimodal models encompass text, image, video, and even audio training data. In ophthalmology, decision-making rarely depends on one input, as we know. A diagnosis might rely on slit lamp images, visual fields, OCT scans, and patient's ocular history. So a multimodal approach is uniquely positioned to handle the clinical intake and management. Rather than treating these data streams separately, these can learn how to relate different data types during pre-training. So as you can see on the graph to the left, the number of LLM-based publications in ophthalmology has been increasing since April 2023, with much of the literature focusing on controlled formats like board exam-style questions, which may not always reflect the ambiguity or complexity of real-world clinical cases. Subspecialty areas like uveitis and neuro-ophthalmology are often underrepresented, and prompts tend to be very simple and generic. There are very few studies that have assessed how models handle open-ended questions or image interpretation, both of which are critical in clinical practice. So our study's objective was to evaluate GPT-4's diagnostic and management reasoning in complex ophthalmology cases by varying access to text and image-based case data and comparing its performance to board-certified ophthalmologists. So this was a cross-sectional study using GPT-4 with vision capabilities. We tested the model on 422 published clinical challenge cases, which included the textual clinical vignette, as well as associated ophthalmic figures. For each case, we assessed GPT-4 on two tasks. Firstly, providing an open-ended diagnosis and secondly, selecting the correct next management step from a multiple choice list. A total of 10 ophthalmology subspecialties were covered with their distribution depicted on the top right figure. And we compared GPT-4's performance with 3 board-certified ophthalmologists, a general ophthalmologist, glaucoma specialist, and a medical retina subspecialist. Each comparator reviewed 47 randomly selected cases, and they were given the same input as the model did and worked independently to have an answer. And to fairly compare model and human performance, we recalculated GPT-4's accuracy on just that subset of cases that was used in human benchmarking. The figure below shows how we tested the model under 3 prompting conditions. The first arm was a text-only prompt containing the case title, and figure descriptions. In the second arm, we prompted GPT-4 with a text prompt, including the case title, and figure descriptions along with their associated figures. And figures were typically external photographs of pathology or various diagnostic photos. And the third arm included the vignette and the figures, but we omitted the figure descriptions. So this allowed us to sort of isolate how well the model could interpret images alone without any textual guidance describing it. So GPT-4 was accessed through the web-based UI rather than the API. So the default hyperparameters were used, but since OpenAI does not often publish this, the temperature is believed to be around 0.7. To reduce bias, each case was prompted in a new chat. We disabled the memory feature, and human graders were blinded to the correct answers and model outputs. We use the Plan and Solve Plus prompting strategy, which is essentially designed to elicit stepwise reasoning. And the model was instructed to analyze the case, generate a working differential, then select the most likely diagnosis. And if the model didn't provide a clear or specific diagnosis, we usually followed up with a prompt that asked it to commit to a single best diagnosis. So in terms of grading criteria, we graded answers using a strict criteria where both the general category and specific etiology must be identified. So a uveitis was not sufficient if the actual answer was herpes simplex uveitis. For next step questions, the model or human had to choose one correct answer from 4 options, and then all responses were reviewed by at least 2 independent graders, and discrepancies were resolved via consensus. And to the right, you can see a sample prompt and prompting algorithm. And here's what sort of a typical prompt would look like. There would usually be images interleaved with text into one prompt. The textual prompt then included the instructions, case title, case itself, multiple choice options, and descriptions of the figures if applicable. And we did not perform any preprocessing or annotations to the images themselves. And then we graded responses as correct, incorrect, or unclear. And this was our protocol to deal with unclear options. If it was unclear a second time, then it was deemed incorrect. So our first conclusion was that figure descriptions were associated with more follow-up prompting. So each case included on average just over 2 images. And we found that GPT-4 was more likely to give an uncertain or vague diagnosis when figure descriptions were present. It required a follow-up prompting in 51.7% of cases compared to just 41.2% when descriptions were omitted. And at the subspecialty level, follow-up prompting was especially common in pathology and tumors cases when only figures were used, and in glaucoma cases when descriptions were included. Now, despite these differences, there was no significant impact on the final diagnostic or next step accuracy. So when GPT-4 was prompted with figures only, its diagnostic accuracy also dropped significantly to 38.4% compared to 47.9% with text-only prompts. Next step performance, however, remained relatively stable, where there were no significant changes when we moved from the text-only arm to a figure-only arm. And subspecialty analysis also showed the greatest drop in diagnostic accuracy for pathology and tumors as well as pediatrics when we made this change. So Figure descriptions also restored diagnostic accuracy back to its baseline text-only level. So it rose to 49.3%, which was no longer statistically different from the text-only arm. And compared to figures without descriptions, this was a substantial improvement, and the difference was statistically significant. Meanwhile, there was still no meaningful change in next step performance. Also, at the subspecialty level, the meaningful improvements were in cornea and neuro-ophthalmology. Now, when we benched GPT-4 on 47 case subset across 10 subspecialties, we found that for diagnosis, GPT-4 achieved 40.4% accuracy, which was statistically similar to two clinicians at 51.1 and 48.9%, but significantly lower than the highest performer. Next step accuracy was 46.8%, again comparable to the lowest human score, but significantly lower than the other two, which were at 78.7 and 78.3%. Inter-rater agreement among human graders was moderate, with Fleiss's kappa values of 0.43 for diagnosis and 0.51 for next step decisions. And overall, we found that GPT's performance approximates that of the lowest performing ophthalmologist for a given task, but remains below the other two evaluators. So how do we actually interpret this performance? Firstly, we found that GPT-4 relied more on text than image-based data, which makes sense. The model is fundamentally text-driven, and when figure descriptions were removed, we noticed a large drop in diagnostic accuracy. And so when those were returned, the diagnostic accuracy improved back to its baseline. And this supports the fact that even with multimodal input support, GPT-4 performs best while processing text. And it might also reflect how these models were trained in the first place, with far more textual data than visual data, in particular, the very specific subspecialty images that would have been inputted from these cases, because these were also rare cases. It's understandable why it might not have been able to interpret the images correctly. Secondly, GPT-4 struggled with multi-image prompts. It often treated multiple figures as a single composite, confused different anatomy, laterality, or different imaging modalities in the first place. And so it shows that there's a sort of lack of ability to parse between visual context panel by panel, because some of these multi-panel figures were simply partitioned by a white bar. So differentiating where one image ended and another began was a struggle. Thirdly, performance varied by subspecialties. So it did worst on pathology and pediatrics, which may have been underrepresented in the training data as well. Fourthly, next step performance was relatively stable across all different prompting arms, unlike the diagnosis, which kind of gives us a clue that multiple choice formats, which are text-based, help anchor the model's reasoning even when there were differences in imaging presence. So although GPT-4 exhibits high performance in structured ophthalmic tasks, there are limitations that remain, as we found in this study. So these include, restricted reasoning depth, inadequate image-text integration, and a propensity for hallucination. As the field progresses, there are two major trajectories that are emerging. The first being models explicitly trained for multi-step reasoning. One example being DeepSeek R1. You can also look at OpenAI O1 or O3 now. There's also Gemini's 2.5, which also is considered a reasoning model. And there's also retrieval augmented generation, which anchors output in verifiable external data. And I'll talk about both. So currently, most models that we use today, like GPT-4, are based on the causal decoder-only transformer architecture, meaning that they generate output by predicting one token at a time, and they're conditioned only on the tokens that came before. These models are exceptional at fluency and coherence, but they were not inherently designed for structured reasoning. So to encourage more logical behavior, we use specialized prompting strategies like the Plan and Solve Plus, which can help scaffold a reasoning format. But regardless, these models have important limitations in clinical contexts as well. First, they frequently hallucinate, producing factually inaccurate content that may sound plausible. They might also lack internal checkpoints, and there's also no self-evaluation or error correction as they go about their reasoning process. So to address the limitations of standard language models, a new class of reasoning models has emerged. These models go beyond next token prediction by introducing explicit mechanisms for logic structuring and self-evaluation. They first use reinforcement learning to reward logical coherence and penalize contradictions. They incorporate chain of thought prompting directly into their training, which encourages multi-step problem solving. And they also include self-correction loops, which are termed aha moments, where the model reflects on its answer and revises reasoning before finalizing its response. They also use techniques like rejection sampling, which selects the best of several candidate outputs, as well as mixture of experts routing, where only the most relevant reasoning pathways are activated. So the result is essentially a model that not only answers correctly more often, but it shows us how it got there, which is crucial for transparency in clinical decision support in the future. So even with a reasoning optimized model like DeepSeek, these remain constrained by their training data. They can't access new information unless they search for it or verify facts that knowledge which was already encoded during pre-training. So retrieval augmented generation addresses this by retrieving relevant documents at inference time, meaning when the model itself was prompted. So this figure just briefly shows how RAG works in practice. It starts with a query encoder, which converts the input question into a dense embedding, which is then used by the retriever to search a vector database, which could be populated with whatever you as the user would like, a guideline, textbook, curated ophthalmology, papers. And so the retriever output consists of the top K most relevant passages. And these are then augmented into the prompt along with the user's original question and passed back to the generator, or LLM in this case, which produces the final response. There are several key benefits to this approach. Obviously, it would reduce hallucinations, improves accuracy, and enables specialization without the sort of resources financially and computationally required to retrain a model from scratch. So essentially, RAG allows LLMs to reason with evidence and not just from prior memory. So lastly, we can think of AI in ophthalmology, or really any field in medicine, as a continuum from generalist to specialist models. On one hand, we have general foundation models like GPT. These are the most accessible. They accept natural language queries, they require no fine-tuning, and they have low computational demands. In fact, we use this at minimal computational costs. That said, these models shine in patient-facing roles. They can automate intake, triage, and summarize patient histories. In the middle are fine-tuned foundation models, which the quintessential example in ophthalmology being RetFound, which learns generalizable retinal features applicable across tasks without requiring task-specific labels. So it offers a nice balance between flexibility and performance, and they're adaptable across different subspecialties. On the other hand, what I mentioned at the beginning of my talk, which are convolutional neural networks, and these offer the highest performance, but are limited in scope in terms of the task that they perform, and they require lots of annotated data to function optimally. Both these models have potential applications in telehealth, primary eye care, and diagnostic and predictive reasoning. And we believe the path forward will be to continue testing the latest reasoning models, optimize RAG pipelines, because again, simply adding more and more information can actually overwhelm a model and result in worse performance. And further exploring agentic AI technologies that can use different features like search function, image interpretation, deep reasoning, autonomously to complete a predefined task. So thank you all for listening, and I look forward to further discussions.
Awesome. Thank you so much, David, for your very interesting talk. So now we have the 10 minutes for questions. Adjudicators, please feel free to unmute and share your questions directly.
I'm happy to go first this time. So again, great presentation, great oral communication, and the slides look wonderful too. I had kind of two questions. The first one's very quick. Did you have a motivation clinically for zero shot as opposed to like maybe feedback or like in context examples? I forget if you mentioned this.
It's an excellent question. The main motivation was that previous studies and studies that we had performed as a research team had found that zero shot did perform better. But I see the logic in multiple prompts sort of back and forth to see if we can get to the right answer. I'll also mention that it kind of did turn into a non-zero shot study once there were unclear diagnoses provided. So there was some follow-up in the sense that we had to force a correct or incorrect diagnosis at one point. But totally agree that that's something worth exploring in future studies.
Got it. Yeah, I think if you're purely trying to improve performance, definitely like in context example, and you outline the reasoning stuff. So these are all great avenues. A second question is around like I think it's really interesting that you found these differences with the depending on the input, like the image versus text. For the text plus image arm, so when you say text plus image, does the text still contain, so this was like the worst performing arm, I think.
Correct. Yeah.
Yeah. So when you say so text, so you're still, so did you think about a setup that's like image only almost with like minimum? Is that the same as arm three or is that a,
It's a good question. Thank you. Essentially, Arm 3 was the clinical vignette, and within the clinical vignette, there's usually a description of the image as well, just to say Figure 1A shows this finding. So we'd remove those, but we kept the case itself, just because without the case and only images, because these are rare cases and they're published because they're rare and sort of the weird and wonderful in ophthalmology, we felt that the performance would have been low, and as well we wouldn't have been able to ask for a next step in management since the questions that were offered were multiple choice. But certainly with the same database, it's totally possible to simply input the images and see what happens.
got it.
Yeah.
Okay, thanks. That clarifies a lot. I think the last thing, I'm just going to put a paper in chat that I think might be relevant. I think there's some work that kind of discerns in multimodal LLMs, like where preference is given in terms of, I guess, inference, like the text or the image itself, which I think your work kind of replicates some of their findings, which is basically that text, there's a preference where the models seem to pay attention more on text. So just forwarding it in case you find it useful.
Thank you.
No problem.
I can go next. We'll go in reverse order, maybe. I don't know. Excellent presentation. I agree. It was very clear, very concise. Good work. I found it funny as an ophthalmology patient. I probably don't want an AI performing like the worst ophthalmologist in your sample. It's probably not what I want as a patient, but we have work to do. My question is actually also about the image versus text. So I may have missed it, but who produced the text? And could some of this bias have been as a result of who created the text, and could this have been improved perhaps?
Totally. So all the text was published clinical challenges from JAMA Ophthalmology. So there's a pre-specified format which is used for all cases, where there's the case description and a brief history of the patient's case, along with what is the best or what is the most likely diagnosis or what is the diagnosis, and then multiple choice for what is the best next step of management. So it's certainly possible that performance might vary based on how things were written. In fact, we noticed that sometimes the title of the case was revealing of the diagnosis, even though it was designed to be as sort of like a quiz or trivia. So in some cases, we actually had to remove the case title, even though in some of these arm 1 and arm 2, there was case title. But we did a lot to sort of mask as much as possible and account for things like that. Yeah.
Okay, thanks. So, I mean, I think it all brings to light of when you're training these models, what is your reference standard, and how reliable do you think that reference standard is? You're comparing it against what you're calling a gold standard, but it may not actually be a gold standard at all. And I'd be curious to see what those 3 ophthalmologists, when they looked at the images, what they would have written as text instead, and would that have changed the functioning of the model?
Yeah, and whether general ophthalmologists, this was more beneficial for them, or was it something that provided more confusion? I mentioned there was a retinal subspecialist, a glaucoma subspecialist. Did they perform best on their own subspecialty, or was it, was the AI helpful in any way for them to see it as like a future assistive tool? Are
you going to try to replicate this study with other LLMs, Grok and Gemini and others?
Yeah. So we actually replicated. It's going to be published soon, but with DeepSeek on the same data set. and we found that the performance essentially it almost doubled. So it was around 80 something percent. So with DeepSeek and these other reasoning models, it's certainly possible that data leakage could have occurred because we did, it's on the internet and it could have been incorporated in its trading data one way or another. But as I mentioned in the discussion with these reasoning models, it's essentially what you have is a thinking out loud stream of consciousness thought process of how to reason through complex problems like this. And in many cases, reasoning took as long as 30 seconds, which is a lot for these types of studies or these types of models, which kind of goes to show that there is some thinking that goes behind making a decision like this. And when we're thinking about explainable AI or transparency, it's nice to sort of have sort of someone, not someone to blame as much as kind of understanding where these conclusions came from when a model spits out an output for us.
Agreed. Thanks.
So yeah, I think my question or comment goes also in what you just have discussed a little bit, because diagnostic performance is quite low, but it can still be useful, for example, in cases where the ophthalmologists are not doing well. So if you just would take the parts or the images where the ophthalmologists are unsure and so on, if there you would get, say, 50% performance, it would not be bad because half of the unsure cases would be solved. However, if the 50% performance of the AI would completely overlap with the ophthalmologists where they are correct, then AI would be totally useless, or at least the current version. Did you examine which cases sort of the AI does well and where it fails?
It's a good question. So we didn't for this study, but as Austin did in his first study with checking sensitivity, specificity, F1 scores, we wanted to do something like that with this study. The problem with these cases was that each one was completely different and they were all rare cases. And so if we had wanted to kind of assess the performance through sensitivity, specificity, and so on, we would have had to focus on one single diagnosis, for instance, like a glaucoma, and see how it performed in that way. But looking at the questions that would have gotten incorrect would have each been different from different subspecialties. But looking at, for instance, here, there were different subspecialties with different performance, but definitely to your point where correlating or trying to understand were there common mistakes made both by clinicians and by AI models, potentially hinting at an unfair question or a very difficult question, or even a deficiency in our knowledge base and our understanding of the literature, would be an interesting next step.
Or specific image features which do not have anything to do perhaps with the disease, but which can make diagnosis more difficult. So I think it would be good to dig deeper into what's actually happening instead of sort of having the the overall numbers, but looking actually in detail what's happening. I think it would be good to analyze this a little bit further and then to see also when you then think about improvements, because you have shown at the end a lot of good ideas how to improve it. If you know what's going wrong or where things, in which case it goes wrong, then you have an easier pathway forward what to improve.
I agree, 100%. Thanks for your feedback.
Okay, that was all. Thank you.
Awesome. Thank you, everyone. And thank you to our presenters, Austin and David, for sharing their research with us. And again, huge thank you to our adjudicators, Christopher Sun, Kamil Uludeg, and Eric Benchamal for their time and valuable discussions today. And thank you to you guys who attended our trainee rounds, and hope you guys enjoy your afternoon and see you next time.